Greetings to respected faculty. I am Lasya Mandapati from CSC AI&ML B section. My roll number is 24951A6686. And today we will be discussing one of the foundational topics of probability theory, sample space and events of a random experiment. Probability is not just abstract mathematics. It underlies real-world processes, from weather forecasting to financial risk, from machine learning to everyday decisions like predicting traffic. And the building blocks of probability are the concepts of random experiments, sample space, and events. In this lecture, we'll define these terms clearly, explore different types of sample spaces and events, and connect them to practical explanation. By the end, you'll see how these basic ideas form the foundation of all advanced probability and statistics. Probability is the study of uncertainty. It provides a mathematical way to describe and analyze situations where the outcome is not certain. Every probability experiment begins with three key components. First is the random experiment, which is any process that produces an outcome we cannot predict with certainty, such as tossing a coin or rolling a dice. Second is the sample space, the set of all possible outcomes of that experiment. For example, the sample space of a coin toss is heads and tails, while for a dice roll it is 1, 2, 3, 4, 5, and 6. And lastly, the third key component is the concept of events, which are specific outcomes or sets of outcomes within the sample space. For instance, rolling an even number when throwing a dice is an event. These three elements, random experiment, sample space, and event, form the foundation for all of probability theory. From them, we develop methods to calculate probabilities and apply them to real world problems. So, what exactly is a random experiment? A random experiment is any process that can be repeated under identical conditions and whose outcome is uncertain. Think about tossing a coin. The process is well defined. Flip a coin once. The possible outcomes are heads or tails. But before you actually toss, you cannot predict with certainty whether it will land on heads or tails. The same is true for rolling a die, drawing a card, or measuring rainfall in a day. In each case, you know the possible results, but you cannot guarantee which one will occur. This concept of random experiment is at the heart of probability theory. Let us examine the key features of a random experiment more closely. Uncertainty. The outcome cannot be predicted with certainty before the experiment is performed. Well-defined outcomes. Even though uncertain, the outcomes are precise and unambiguous. Repeatability. The experiment can be repeated under identical conditions. Assignability of probabilities. We can meaningfully assign probabilities to each outcome. Take tossing two coins as an example. We cannot know in advance whether we will get two heads, a head and tail, or a tail and head, or two tails. But the outcomes are clearly defined and can be assigned probabilities. By contrast, something like the time of sunrise is predictable and therefore not considered a random experiment. Once we have a random experiment, we can define its sample space. The sample space S is the set of all possible outcomes of the experiment. Each possible outcome is called a sample point. For example, tossing a coin, the sample space is a head and tail. For rolling a die, the sample space is a collection of the numbers from 1 to 6. Notice how the sample space captures every possible result of the experiment. It can be finite like in coin tosses or infinite like measuring the exact time until a bus arrives. Sample spaces can take on different forms. Let us categorize them. Finite sample space. It has limited number of outcomes. For example, rolling a die has 6 outcomes. Infinite sample space. contains infinitely many outcomes. For example, the time until a bus arrives could be a non-negative, could be any non-negative number. Discrete sample space. Outcomes are countable even if infinite. For example, the number of outcomes arriving at a shop. Continuous sample space. Outcomes form a continuum, meaning they take values in a continuous interval. For example, the exact height of a person or exact rainfall in a day. This distinction between these sample spaces matters because different probability models apply depending on whether the sample space is finite, discrete, continuous, or infinite. Now, let us move to events. An event is simply a subset of the sample space. In other words, it is a collection of outcomes that share some property. For example, in rolling a die, the sample space, like we've discussed before, is this list of is the list of numbers from 1 to 6. An event might be getting an even number, which is 2, 4, and 6. In tossing 2 coins, an event would be getting 2 heads. Events are central to probability because we usually assign probabilities not to single outcomes but to these subsets. Events themselves can be classified into several types: simple event, compound event, sure event, and impossible event. Let us look into these in further detail. Simple event. These events contain only one outcome. For example, rolling a 4. The only possible event is a 4. Compound event. These events contain more than one outcome. For example, rolling an even number on a die. You can get a 2 or a 4 or a 6. A sure event. The entire sample space. For example, when rolling a die, the event of getting a number between 1 and 6 is certain. Impossible event. The empty set, meaning no outcome satisfies the condition, like rolling a 7 or a 9 on a standard die. By categorizing events, we can apply probability rules more symmetrically. Two more important concepts are mutually exclusive events and exhaustive events. Mutually exclusive events. Two events are mutually exclusive if they cannot occur together. For example, when rolling a die, the event of rolling a 2 and the event of rolling a 5 cannot happen at the same row. If you look above, this figure depicts two mutually exclusive events. Exhaustive events. A set of events is exhaustive if, taken together, they cover the entire sample space. For a coin toss, the events head and tail are exhaustive because one of them must occur. Together, mutually exclusive and exhaustive events partition the sample space, dividing it into non-overlapping parts that cover every ring. For every event, there is a complementary event. If event E occurs, then its complement E dash is the event that E does not occur. Formally, E dash is equal to S minus E, meaning that all outcomes in the sample space except E. An important property is that the probability of E plus the probability of E dash is equal to 1. In words, either the event happens or it doesn't. Complements are very useful in calculations because sometimes it's easier to find the probability of not happening and then subtracting it from 1. Now, we come to the difference between independent and dependent events. Independent events. The occurrence of one does not affect the probability of the other. For example, tossing two different coins. The result of one coin has no influence on the other, and its formula is given as in the probability of the intersection of A and B is equal to the probability of A into probability of B. Dependent events. The occurrence of one changes the probability of other. For example, drawing two cards without replacement. If the first card is an ace, the chance of drawing an other ace decreases because one ace has already been removed. The formula for this is that the probability of A intersection B is equal to the probability of A into the probability of B by A. The difference, however, is crucial. Independence means no influence. Dependence means probabilities shift. You can think of independent events as happenings in the separate worlds, whereas dependent events are connected by cause and effect. These concepts are not just academic, they show up all the time in real life. For example, weather forecasts. Rain or no rain is an event in the sample space of possible weather. Traffic. The number of cars passing a checkpoint in 1 hour is a random variable based on a sample space. Customer arrivals in a store or calls to a call center, games and lotteries are all other examples as well. By thinking in terms of random experiments and sample spaces, we can even make sense of these uncertain outcomes and manage risks much better. Applications extend into many fields, like science and engineering, where reliability testing of systems and predicting failure probabilities. In computer science, it is used for randomized algorithms, simulations, and machine learning models. In finance, it is used for stock price movements and insurance risk models. In medicine, it is used for clinical trials, where patient outcomes are uncertain but modeled probabilistically. This is why mastering these basics is so important. They're not just theoretical but essential for modern applications. To summarize, a random experiment is a process with uncertain but well defined outcomes. The sample space is a set of all possible outcomes. An event is any subset of that sample space. Events can be simple, compound, mutually exclusive, exhaustive, complementary, independent, or dependent. These concepts are the building blocks for all of probability theory and its applications. If you understand these fundamentals, you are ready to move into deeper probability topics like conditional probability, random variables, and distributions. Thank you for your attention. I hope this lecture has given you a clear picture of random experiments, sample spaces, and events. These simple but powerful ideas form the foundation for everything that comes later in probability and statistics.